Alright, time for another draftphysics.com video presentation. So, two slit stuff. Photons, wave versus particle. I'm basically arguing that I can destroy any kind of notion of a wave theory, that the facts make it just unreasonable to believe that this is about a medium and about waves spreading in all directions or any of that kind of stuff. This is about rays of force, discrete bits of force, and the fact is that the slits are doing something kind of obvious. They're surfaces, and the surfaces are disturbing the photons, and the photons can be reclamated. They can be restored to their previous condition. They're just a pattern. You can break the pattern, and then you can remake the pattern. It's that simple. So anyway, on with the show. So the standard, this black isn't very black, but starting to run out of little crayons. Anyway, alright, so here's the standard two slit, okay, and they create conditions. They say, okay, the waves are going in, and they're going to create two little waves here. So this is the standard Young type drawing of this idea that it's the waves interfering in space here, okay, that's causing, okay, there to be places where you get a bar of light and then an empty spot in a bar and an empty spot in bars. Okay, now the real, okay, double slit pattern has two patterns in it. Now, 90% of the videos online don't talk anything about the fact that there's two patterns here. You can sort of see two patterns. There's the spacing between these nodes, and then there's spacing here. There's places where there's no light, okay, and those reoccur at specific geometric locations. Now, conventional physics, this drawing can't account for that. Two waves can't account for the two patterns. It's just not enough information. There's no way to make it sensible. And so there has to be a better or different theory of what's happening. Now, the way they get around this, the Richard Feynmans and the rest of them, is they basically negate the existence of the two slits by saying these are infinitesimally small slits. So they make the slits either really, really tiny, so small that there's not a wavelength of difference, which means that the geometry for the slit, it would be impossible from these two surfaces. They put them so close together that you couldn't make a wavelength of difference in the length of a line. No line, even this line, they can't have a wavelength of difference because there's not a wavelength of difference in the size. Now, obviously, you can go quite a bit bigger than as small as the wavelength of the light, and you'd still get a few nodes, like 2 or 3. And that's going to be certainly less noticeable. But anyway, yeah, so you could have a couple of positions where this would be on, then you'd have a big off, and then a big on. Anyway, or the other thing they do is make the impediment. If you make the impediment really small, like a thread, in the two slit, you're doing the same thing. You're taking two potential sources, and you're putting them so close to each other that they become one source. So it only becomes the three-source experiment rather than the four-source experiment. So you're basically negating the existence of the slit and really just creating two distances. Alright, two potential distances. You just have this distance and this distance, which will be in the same on both sides. So you only have two distances between any 2 point sources. And it's all about distances because that's what the math is. The math is just geometry. It's just saying, is there a wavelength of difference in the length of a line? So you're just looking for this wavelength. Here's the wavelength. You're just looking for that difference in any line reaching any point. So if I can draw a line to any place on the slit and create a wavelength of difference, I am saying that I have a full wavelength. Means that what you've done is taken, even if you accept the silly wave description of a photon, you're saying that you want to put them a full phase out of phase, so that they will still be continuous in terms of looking the same. So you're saying you don't want this, okay? You don't want an asymmetry in the waves. You want them symmetrical. And the argument I would make is the reason why you want them symmetrical is what you're really making a photon is you're taking a piece of one of them and combining it with pieces of other ones. So you're really making a photon out of different pieces. You're just looking to restore a pattern. So putting them a full wavelength is really just saying that I'm firing bullets at a specific time, 1 second between them. And I want all the guns to fire them at the same time because I want the bullets to land at that period, 1 per second. And so if I have guns that are firing off that 1 per second, then those are negated, essentially. So you're just saying the only ones that count, the only ones that are going to add energy to my system or whatever I'm doing, are the ones that hit at that sequence. Alright, so we'll erase this and diagram the real story. Alright, should be back. So I would argue that a photon is really quanta, okay? As Einstein kind of pointed out, there's a fixed amount of energy, and the fixed energy is really based on the fact that the photon is a composite object, that it's made of little bits, and the little bits have a distance between them, and that's the wavelength. Alright, now I won't get into polarization, but yeah, you can just sort of understand that I could simulate, okay, a frequency, okay, by having a frequency, just by shooting bullets at a frequency. So if you understand a photon as something like that, okay, a mechanism that is made of a collection of little bits, they have to hit a surface, and that surface will interpret it as a photon if it has this frequency. And so I won't go into exactly how electricity works, but that's how you create electricity, is you push an electron, and to push the electron you need to hit it more than once. You need to give it a little extra energy, a little more energy, a little more energy. And you're really not hitting the same electron. You're hitting an atom, disturbing its electron. Its electron disturbs the atom next to it. Then you hit that atom and push the electron some more, a little more energy. And that's how you're adding energy, propelling an electron. And you can either move the pressure of an electron through a surface, or you can actually eject the electron if you give it enough energy. And that explains the photoelectric effect and radiation and lots of other stuff. So anyway, so if you understand that being what a photon is, and you can sort of understand that if I take a slits, what do I really have here is I have these surfaces that are covered in electrons. So you can understand that photons and electrons do interact. And so what's really happening is you're sending a bunch of these little bits, okay, and at a consistent frequency, lots of pattern. And what's happening is the ones that go through the middle, they go just straight through. Okay, those photons are undisturbed because they're not big enough. The slits are wide enough to allow photons to get through without their little bits being disturbed. But the catch is the ones that travel near the surface, well, they're going to get scattered. That is, they're going to hit an electron, and what's going to happen is they're really staggered in space. So that is polarization. So it is sort of you need to sort of understand that a photon occupies quite a bit of space. These bits occupy a large area of space, 1,000 atoms of space, and it's where the pattern really is. So only one bit of the photon will hit an electron. All the little bits don't hit a single electron. And one of the little bits will hit the electron. The electron already has a position. It's magnetically held, okay, based on its relationship in an atom. And so it's going to move a certain way because of its own tension. So when the photon hits it, it doesn't move the electron in the same direction that the photon hit it. It doesn't just go straight. It goes in some other direction based on its tension. And so that direction can be almost any direction, you could argue. Now you could argue there might be a tendency for the electrons to move in rather than out of an atom, so that there would be a tendency to go out more than in. But we don't need to go into that either. the point is that you could expect there to be scatter. That is, each little bit, depending on what electron it hits and what position the electron's in, you know, whether the electron is this way oriented to the nucleus or whether it's this way oriented to the nucleus, obviously it's going to move differently depending on how it's oriented to the nucleus of the atom. So anyway, but the idea would be is that you could expect scatter. So at each one of these surfaces covered in electrons, the little bits of photon are going to fly off in all of these directions. And so on your surface, you can have this rational expectation that all these little pieces of a photon are going to end up flying to these different locations. And you basically have a 50-50 chance that a bit from here, or a bit from here, or a bit from here, or a bit from here will be in phase. That is, they'll have the same, they'll be able to restore this condition. All right. Just depending on the path length from the sources. So you're just saying, basically, okay, they're going to get delayed a certain amount because of the electron's motion. That's going to screw them up a little bit in terms of their phase. But that all of that would sort of equal out over a whole bunch of permutations, so it wouldn't really matter. So you're really just saying is you're just going to measure the path length from this location and this location, and then this location and this location, and then this location and this location. So you have 4 sources, and you're really just saying, is it a wavelength of difference in the length of these lines? Because if it's a wavelength of difference, then you've got a chance of restoring the photon. That is, you'll take a bit from, you know, in these different positions. The first photon went in like this, and the other one's like this. Anyway, so you're taking like one bit from one that went the right way, and then this bit from this one that went the right way, and this bit from this one, you know. So you can make the photon out of these 4 different sources. You could expect to rearrange something that looks exactly like a photon, even though it's made of bits of energy from all 4 locations. So what you're really seeing on the screen is a little bar that represents the fact that all 4 of these distances are a wavelength, a full wavelength, are close to it, right? It's either, this whole thing is really just a 50-50 argument. You're either getting to be out of phase or you're getting to be in phase. So you really don't have to be perfectly in phase. You just have to be that part of the triangle, right? And this is the out of phase part. So the in phase part is this, okay, and the out of phase part is this part here, and you know, you're just doing that kind of thing. So the bars are going to be symmetrical, you know, and in reality it comes out that the light bars are bigger than the dark bars, which sort of indicates there's quite a bit of flexibility. You don't have to be perfectly in phase. You can be a bit out of phase, and the photon will correct for that. So one of them could be an inch apart, and this one could be 3/4 of an inch, and this one could be 5/8 of an inch. You know, you can have these different distances, and what basically this is just represents energy. So it just means that you just take the average of those distances and call that a red photon or a blue photon or a green photon. All right, anyway. So it's really these 4 sources. Now, what would the 4 sources represent? So then you go to something like a diffraction gradient. And maybe that's a better way to represent part of this. But the real point to also understand is that you're not really sending it to a flat surface. That's not what the math is predicting. The math is actually predicting the same distance. Okay, this L distance doesn't change. So in the math, they'll use L as the distance from your source the source of the disruption of the photon to the target. Now obviously the L would have to be longer here, and they don't change the L, so the L stays the same. So obviously what they're doing is they're calculating what the pattern will be on this arced surface. And you could sort of understand that if I was to use point sources, you know, these are just point sources. These are like little light bulbs. Okay, so the surfaces are just like new light bulbs, and they're just radiating this light. Okay, so you can sort of understand that the what's going to give it away is the light from this one and the light from this one, because here's the distance, right? Here's the difference in the distance, and all the wavelengths have to be in here. So if I just divide the wavelength into this distance, I'll know exactly how many places it's possible to have a full wavelength of difference. So this tells me exactly how many places it's possible to have one of these bars, the on parts. The on parts are going to be dictated by this difference in distance. And if this is if this distance isn't a perfect wavelength of difference, then this distance can't be a perfect wavelength. So one of the dodges is that they do this kind of thing and say, look, these two waves have to be the same, so this node in the middle has to be an on. All of that's happening inside of 1 millimeter. Okay, this is a tiny experiment here, a big giant surface here. So all of that must be the same stuff as happening inside a tiny, tiny space on the target. And the real pattern is something like this, where you have these two bars. These are all straight lines theoretically. And so you have everything that moves this way, where the two lines go the same direction. Well, anything that's going opposite directions is opposite to what's happening. All the fringe pattern is really made out of things going in the same direction. So all of the fringe pattern is made out of those lines, not lines that intersect. So you could theorize that the reason why the middle node is bigger is because it's really two nodes overlapping. Alright, so that's part of the mechanics that just gives this away. So it was never an infinite pattern that went in infinite space because of the fact that they always used a flat target. Now it'll come out pretty much the same. The round target will tell you what the flat target's going to see. But the fact is because it is round, these nodes change size. They get much bigger, okay, as they get further away from the center. So they're a little smaller here than they are here. And so that's another important fact, not explained by any Young diagram, not explained by any Young analysis, and certainly not in any of their math. All right, so we'll move on to the next argument. We'll use diffraction gradients as the example to the real biting point, the point that really gives it all away. All right, should be back. All right, so understanding it as point sources. So every surface is just a point source. And so again, you can do this kind of obvious analysis and just say, what do I have here when I have these point sources? Well, I have a largest distance, okay, and then I have a shortest distance. So in this case, the shortest distance would be this. Now, there's also a third distance, right? I got this distance, all right. Now, the point would be is that the odds are, though, is that this third distance probably isn't going to be in phase, ever, with the other two. So you're never really going to see the third one. So the argument would be is that the reason why you see the pattern the way you do, the double slit pattern, all right, is because there's not enough energy from either one of the single sources. All right, I shouldn't have put 4 here, but this is always an odd number. So I'll put 5. Now I'll put 4 here. Anyway, so each source, each pair isn't producing enough photons, enough pieces to make a visible photon. And so from this widest source, the scatter from here and the scatter from here, by themselves, they can't make a pattern. They need the scatter from here and the scatter from here to also match, to be in phase. So they need the extra pieces. And you can sort of understand why, by having the 2 extra sources, I'm squaring the number of permutations where I can have a match. So that gets into probability math. But I mean, you're really doubling your capacity, the likelihood of getting a match. It's quadrupling it rather than just doubling it. So the fact that you have 2 more sources really enhances your capacity to make a visible photon. So that's why the 4 sources are necessary, and you can't just make the single slit out of the double slit and have the expectation that you still have the double slit pattern. So anyway, so all you're really saying is okay, this is the one providing the longest distance, is providing the small bars. So these little ones are being provided by this distance. This will tell you exactly how many there be. And again, remember, it's on technically it's on an arc line. Okay, and you're really just saying these are specific locations that you'll be able to create, okay, one of these little bars. And the shortest distance, kind of obviously, the wavelength into a small number gives you a small number. That's creating the nodes. So the nodes are, this short distance is creating light in this whole area, okay? But it's not enough for you to see it without the extra light from these two sources so that make it bright, okay? And so that's what makes the bars. So that's the real explanation for the double slit. It works perfectly. This is about point sources. It's about surfaces, all right? The geometry is the same. The math still works. You just have a better understanding of why the math works. And the math really doesn't work if you try to use the infinitesimally small slit. So you can sort of understand if I move these two point sources right next to each other, I only have, I've converted a double slit, right? If I move this one really close to that one, I move this one really close to that one, I've really eliminated two of the point sources. And I really only have two scatter locations now. And so I've converted a double slit into a single slit. That's why the Young analysis works, is because it's really looking at a single slit pattern because of the infinitesimally small slits. So if you use regular open slits, then you really have 4 point sources, and then you'll create the real pattern which has the envelope in it. Alright. Now, a diffraction gradient. I thought I could draw that in here, but I really can't. So I will pause once again and we'll draw again. Alright, back again. Alright, so the diffraction gradient is just where you're basically just saying I'm going to make a lot of slits, okay, a lot of slits, a lot of little tiny surface interactions, okay, so yeah, you're just increasing the, and so what are you really doing when you're adding more of these little same spaced, they don't even have to be same spaced, and they actually can be crossed in you can do lots of different patterns and create lots of different orientations where you're breaking photons this way and you're also breaking them this way, and you can create all kinds of patterns, all kinds of geometric patterns. But what you're really going to do is just duplicate the source light in different locations, because technically what you're doing is just sending pieces of the image to the different to symmetrical locations, different locations based on the angles of the separation. But so what happens when you add more and more of these little lines? Well, you're really just saying how I'm making more lines, I'm making more places, okay, for it to happen. I'm making a bigger distance, right? So I'm just adding the biggest distance. So when I add all of these up, it's just like the double slit pattern where I drew the the big node and then it has the little nodes inside of it. Well, you're really just magnifying that effect, and you're really saying, well, what's my tiniest little bar I'm making? The tiniest one is these two. Well, in this case you're only using this part because that's where your laser's hitting. So what's my longest distance? Okay, my furthest distance, and that's a bar. Well, what's my second furthest distance? Well, it's this distance and then this distance. Well, it's making a bigger bar, right? A little bigger. And then what's the next distance? Well, it's making a bigger bar, right? Okay. And the next one's making a bigger bar. Now you can sort of understand that these bars won't line up, right? There's going to be places where these aren't lining up at all, like this one here is going to be right in the middle of this one, so that's going to be, they're not going to contribute to each other, and these are going to do the same thing here, right? So I'm not drawing this very perfectly, but you should be able to follow along. And the idea though is that this perfect pattern will reoccur, okay, just like symmetry in all kinds of oscillators. This pattern will exactly reoccur over here, and they'll all line up again. Okay, they'll all be right on top of each other again. Alright, and so it'll be a perfect storm idea where all of them line up at this location. So you're going to get a blob of light there. So you have a blob of light here, you get a blob of light there. And again, it's just geometry, so it's geometry on an arc. And so what you're going to have is another one over here where they all line up again. Alright, and that's all you're really saying is that the photon is made by increasing the number of sources that are sending pieces to a location. And if you increase the number of sources, even though they're sending less light per source, you can make more, you can combine them back into a bright spot again. And all the other locations are just getting pieces. Like some of them line up, but it's not enough for you to see. And these line up, but it's not enough for you to see. It's not enough for you to see. So there's plenty of radiation, the same amount of radiation, that is little bits, are hitting here. It's just less of them are in phase. So the same, number of these little tiny, photon, the little bits of the photon, the quanta, the same number of quanta is landing on all locations. It's just the difference between in phase and out of phase. And that's all that matters to make a photon. A photon is a pattern of little bits. Me sending bits at this kind of pattern, that won't do any good. That won't be seen as light or as any kind of electromagnetic radiation. It won't be able to eject an electron because it's not going to hit the electron. The electron is in a constant back and forth motion. And the idea is, if you want to add energy to an electron, you have to keep adding the energy when it's moving in this direction. And if you add the energy when it's moving back, well, then you're going to destroy the energy. You're going to lose the momentum of the electron. It's going to be lost. And it's going to be, it'll be going, it's like going 25 miles an hour here. It's going 50 miles an hour here. Well, this off one put it back to 10 miles an hour. So you've lost the momentum in the oscillator. You've taken energy out of the oscillator instead of added energy. That's why photons have to have a frequency. That's why they have to, those are really explicit rules, is because they have to add the energy. They have to keep hitting when the electron's moving in the right direction. And if they hit when the electron's moving in the wrong direction, you're not going to eject the electron. You're not going to keep the motion moving forward. You're not going to keep the energy in the system. That is the simple way to put it. But anyway, so you could also understand a diffraction gradient is just about an angle. So if I had one here and I tilted it, and more importantly, if I tilted it away from you, you can understand that the lines on the top here are moving further away from you than the ones at the bottom. And so that they're getting narrower and narrower more quickly. So the length of the line is getting longer as the thing's moving this way. These lines are getting longer than these lines are changing. And so you're basically, by just tilting it, I'm creating the circumstance where I'm piling them up again. I'm getting them in the right orientation where they're all a wavelength of difference because I'm changing the distance they're traveling by distorting the source. So that's why diffraction gradients, it just depends on, you can turn the angle of them and change where you're going to get the image. What location it'll happen at. So, you can also understand it in that way. I think this way is simpler, just to understand that you're really just talking about at what distance are all these sources in phase and at what locations. And there are specific locations where they're all in phase, that they all line up again. Alright, I think that does it. Don't know if there's other details to add, but I don't think they're going to add much. The point is that this is what Einstein spent his, a great deal of his time contemplating, trying to figure out some way to get out of this wave idea. He didn't like the wave idea. He wanted a corpuscular explanation for photons. This is it, okay? This makes sense, it works, it fits the geometry, it fits the math, it explains the phenomenon. And it does it rather decisively. So, you can just keep denying, you can keep, arguing, but the fact is that it explains it much better. There's no need now for bits to go in and out of anything. They don't have to figure out anything. The photon doesn't have to do any math. There's clearly nothing random about it. So it completely blows up any idea that every photon gets randomized by the special random god. As Feynman would put it, you don't like it, tough. Yeah, well, Einstein didn't like it. I didn't like your explanation, and it's not tough. Okay, there is a better explanation, and this is it. The geometry works perfectly. It's, this is a much better answer, just a fact. And we'll just see how many years it takes for the better answer to be accepted. See how scientific the scientists are. See how belligerently they deny the much better explanation. And that's all we're stuck in. So, maybe I'll post this video on YouTube because it's a decisive argument. we're done, okay? It was a fact that the Young explanation wasn't even explaining the double slit experiment, like I pointed out. It was annihilating the double slit. It was preventing the double slit pattern from even revealing itself by the very fact that you made two of the surfaces so close that they couldn't produce photons that could possibly be out of phase. It was impossible for them to produce out of phase photons, because they were too close to each other. So that geometry was already nonsensical in terms of actually doing a double slit experiment. And they've been spouting that rhetoric for decades. And all the other key points of the fact that you can just figure out exactly how many nodes are going to be created by just dividing the wavelength into the distance. The answer is at the surfaces. The phenomenon happens at the surfaces. The whole thing is a mechanical, simple little process. It's just caused by scatter, and it makes perfect sense that that's what would scatter. Scatter is already a known way you bend a photon. We already know that banging photons into electrons will cause the photon to change its direction. And it changes its direction because if you thought of the photon's energy as pushing my hand, so the photon hits this way and pushes my hand, you can sort of understand when my hand pushes, it's pushing the forces that are coming at it. So now it's recreating the photon. The photon isn't the same photon. The same piece of energy that hits the electron isn't the piece of energy that the photon is made out of. So the photon is not an object, it's a composite of energy. Little quanta of energy. So again, this is a quantum theory, a particle theory, a corpuscular theory that completely, not marginally, not just a little bit, but really completely explains what the two-slit pattern creates. It explains the fringes. All the fringe light is created by photons that travel near the surface. Without the surfaces, there's no fringes. So that's already a known fact too. So clearly the surfaces are the game. And what's on the surfaces? Electrons. And what does photons do when they hit electrons? They change direction. I mean, it's that simple and that obvious. I mean, in hindsight, it's so obvious. I am sort of embarrassed that it took me 10 years to wiggle through all the bullshit and try to make a rational theory out of the nonsense they tell you. Alright. I don't think there's some other little point I wanted to raise, but it's probably not necessary because I've given you more than enough to figure this out. The other thing that gave it away sort of was the radar experiments and the radio experiments. Because all those experiments were basically saying, hey, you know what? This fringe pattern is exactly what jamming would look like. I mean, if I jammed a signal, deliberately tried to jam a radio signal, it would do exactly the same thing. I can't pick up two radio stations at the same time if they're out of phase. So this isn't about destructive and constructive interference. It's about breaking a photon, that is rearranging it, taking the bits and moving them out of position, and then just remaking it again. So you just break it, and then you remake it. It's just a pattern. You mess up the pattern by having the photon go through an obstacle course, and then you just say, well, look, if I throw all those bits against the wall, because I only 50-50 rearranged them, I took their phase and made them out of phase in very specific ways, then I can just put them back in phase. And that's when you get into the other optics of polarization and polarization film, and the fact that you're not destroying any of the photons. You blocked all the photons by putting the two filters this way. You really didn't block them. You just broke the phases. Okay, none of the photons are being absorbed by the filters. None of the photons were destroyed. No elements of the photons were destroyed. All you've really done is just break all the phase. And you can get the photons back by putting another filter in. You can get, a third of your photons back. Obviously, they weren't broken if you can get them back again. All right. Yeah, that's probably enough of that. So there's a Brozo video that no doubt has probably some good images of single and double slit patterns, but he's probably got a bunch of crap rhetoric piled in there, so we'll just see what the video is. Now, I guess I can do that from here. I can just load this and unload that. Alright, so let's see what he's got.
I counted the number of fringes per metre, which I've noted on the end for my own benefit. So the 100 micron gave 42 fringes per metre at this distance. The 200 micron gave 95 fringes per metre. The 300 micron gave 150 fringes per metre. And the 400 micron set gave 210 fringes per metre. Now, unless it's an error on my micrometer or something else, it does appear that the number of fringes per metre increases exponentially, only slightly. In other words, you don't get double the fringes when you go from 100 microns to 200 microns. Yeah, that's 200. You get more than double, so 42 double, would you expect that to be 84, but no, we get 95. 200 microns.
Yeah, well, again, these are Stephen Bro experiments, so you know, how seriously we can take those marginal differences, I'm not going to worry too much about. I mean, it's clearly 95, you know, 85 to, I mean, 45 to 95 to 200. So yes, that's not exactly a huge exponential growth. And the clear indication is that if you do the division and the numbers, the problem is, see, he's measuring, so he's denying a fact that he you know, was so aggressive in arguing. So the fact is that the fringe sizes change. Okay, so on the sides, the fringes are big. As you go in, they get smaller and smaller. Now, I don't know what the percentage is, right? So I'd say that the fringe at the peak is probably 1/3 the size it is at the base. Okay, and that's just because of how circles work, right? I mean, circles, when you know you're going more this way, you know, when you're going this way around a circle, you're moving more this way than you are this way here. And then you're moving more this way than you are that way, okay, when you're going down. So that's why the fringes are distorted, is because of what happens with a circle. So there's your explanation for the difference, is that when you're making them smaller, there's going to be more in there because they're smaller based on how big they're going to be at the base, so you're getting a different number of them. The total spread of them will be different. Probably the explanation. But anyway, let's go to further in the video.
Micron slits made with variable slits. 100 microns. A 100 micron slit made with a variable slit. Film from about 18 inches away. Made with 100 micron variable slit.
So it looks like he built this thing, so I wouldn't be too sure those numbers are exactly accurate, but I'm sure that it's close enough in the sense that whether it's 50 and 100 or whether it's 30 and 60, doesn't really matter. I'm sure twice the distance is twice the distance.
100 micron variable slit. Each division is 10 microns, so 10 times 10, 100. A tenth of a millimetre. The black marks on the top line, they mark the minimum of the 100 micron variable single slit. Immediately below that is a pattern from a 100 micron impediment, like so. It's immediately noticeable that the impediment is a lot clearer pattern, a lot more distinct. Same fringe width obviously as the single slit, but a lot more distinct, film from an angle obviously.
So this is basically pointing out it's about the distances between the surfaces. So he's got an impediment and he's got an opening of the same distance, and he's putting the patterns on top of each other, and they're the same size because the difference between the surfaces is exactly the same. And the reason why one pattern is more distinct is because one pattern is not getting washed out by all the light that goes straight through the opening. So obviously the one surface is kind of a better fringe pattern because it doesn't have a big blob of light, you know, hitting the surface. Alright, see what else he did.
Single slits. The green markings of the previous one from the impediment aren't really visible, are they? My markings aren't visible in the dark. The black ones are. Okay, a 300 micron single slit, 300 micron single slit made with a variable single slit.
So I'm sure what's in here is basically the basic idea, okay? The further away the 2-point sources, the smaller the nodes get, the little dots of light. And the closer they are to each other, the shorter the distance between the point sources, the fewer bars there's going to be, so the wider and longer they'll be. So I don't think he's disagreeing with any of that. So.
Okay, so that's the 300 micron single slit duly marked up. Here it is. There's evidence of it. Oh. Been a bit knocked, okay. That's actually 32. So that's actually 320 microns, but the difference gets less and less with these very narrow fringe widths, but anyway, that's annoying. It drops, I forgot to check it. Oh well, just for reference, I'll correct it. I'll put it bang on 300 and do it again. Okay, hope that's okay. 300 micron, try again. Okay, let's compare. That's actually 300 microns. Oh, should I mark it? Yeah, come on Steve, stop being lazy. So that's actually 300 microns. The previous one was 320 microns. My apologies.
Right, doesn't really matter because what we're really, there's another factor that's messing up any of these markings and all the rest of it is the fact that the light bars are bigger than the dark bars. Theoretically they should be the same size. The dark spot should be half, of half the amount of space should be filled with darks, but it doesn't work out that way. So, that's another limitation. So I don't know what he's marking for, but you can clearly see that there's a distinct pattern here, and the pattern is the further away the surfaces are, the smaller the nodes.
October is classic double slit pattern, that is. I must admit, I'm not 100% confident of the declared slit widths of these so-called professional slit.
Yeah, so now he's admitting something I found kind of obvious, that the numbers weren't very good. You could almost see it. I mean, you looked at it with a magnifying glass and you said it was saying it was 1/10 of a millimeter, and you looked at it and you're like, that's like 1/70th of a millimeter. But whatever.
Because I've checked my micrometers as many times as I reasonably can, and this appears to be pretty bob on, comparing again, coin widths and such like that, checking coin thicknesses and such like. But these landslides, I'm not 100% confident of the declared width on these.
Incidentally, the time I was filming this, May 2020, that was when Gary was telling me that my...
2020, so he's waited 2 years to publish this? I mean, insane, right? I mean, just crazy. So why did he keep this all a big secret? Oh, that's right, because it basically was affirming everything I was saying. What a scumbag. All right, well, let's hear what he's got to say. His little gripes.
Information was dopey. When I was trying to give him the information about these slit dimensions, the beam measurements.
Yeah, whatever. Like I said, frankly, how could I trust you about anything? Why would I be interested in anything you had to say, you lying sack of shit? You're propagandizing, trying to force results to fit your theory. Why the hell would I have any interest in your participation? So I made a theoretical argument, okay, and it stands, and it does fit the evidence. And that's all I give a shit about, retard. I don't need your marginal participation as an experimentalist, and it is quite marginal. It's suspect in every way. The very fact that you don't publish most of the experiments you don't publish them because they don't affirm what you want them to say. And that's a fact.
A bit of a memory loss or something like that. Because he has suffered from Lyme disease, hasn't he? And I have heard recently that can cause...
So look at all this bullshit. So, this bullshit speculation that somehow my brain is defective. Yeah, I had Lyme disease 10 fucking times. And the fact is, I'm still 500 times the man you are. I'm still doing things so much more logically and productive than you are. You're sitting there trying to defend things that can't be defended. You're doing your silly pendulum false oscillation bullshit, and you can't even figure out that the fulcrum can't be oscillating. I mean, you're making the obvious mistakes in your experiments. I mean, just profoundly stupid mistakes. And, correct them. I point out how you have a video called a debunk, and your answer is closer to my answer than your answer, and you leave the video up. I mean, you're just such a liar, a deceiver. Okay, I don't have a defective brain. You have a defective character. You don't have any character. Like your friends, you're a thief and a bum.
So there you go, 75 micron hair. Impediments do seem to produce much better patterns, don't they? Okay. Right, so what it's worth knowing, that 75 micron hair, which should have been the same as all these 375 micron things should have been the same. The lab slide, my micrometer single slit, and the hair. They should all be given the same fringe width, but they're not. Now that the hair is in between the two extremes. The micrometer gives the widest fringe width, the lab slide gives the narrowest, and the hair gives in between. So we've got...
Yeah, it all kind of depends on, I mean, you can obviously understand the hair is going to be a really imperfect surface. So there's going to be lots of averaging. So again, we're back to arguments about how exact the fringe has to be, right? So you're counting the fringe width based on how big the bright spot is, not how big the bright spot combined with the dark spot is. So you're just measuring bright spots. So in that sense, you're just measuring, well, how much... See, any irregularity on the surface means that you're going to have more likely that you're going to be, off that 50-50 thing, you're going to be the 60-40 thing. Like your I hate to have to keep drawing stuff, but your dots are going to be more likely to be off a little bit, okay, because of all those little irregularities on the surface. You're creating, instead of being a perfect 10, this is 9.7, and this one's 9.6, and all this stuff. So your distances are getting further and further off, and it's more and more likely that those variations are going to add up, and you're not going to have a photon. So the number of photons that will be considered in phase, the in phase error, in different circumstances is going to be exaggerated or less. So all you're really saying is if you're just going to measure the size of the bar, okay, that's really cheating, because the size of the dark spot is also important. And if the dark spot's getting bigger and the bright spot's getting smaller, all right, you need to know the total of what a real node would be. Understanding that the node size really has to do with the bright and the dark. You have to have a combination. So you're not even measuring the right thing. Again, failure on a simple argument. You're not measuring the right points to get the accurate node size. Now, I don't know how he made these lines, though. So if he made these lines based on the center of a node, then that wouldn't matter. So I can't say for sure. I probably should watch the video and then make commentary on it. But the point is so he's saying the same. So he shows us how progressively, as you make the slit distance different, you change the pattern. And then he argues, but wait, if I use different materials, they don't have the same size pattern. Well, maybe it has something to do with the materials. It doesn't have anything to do with the absolute truth that in theory, okay, if the materials are the same, the pattern is symmetrical. That is, the further away the point sources are, the surfaces, the thing interacting. So again, you're just sort of cheating the argument. But go ahead, do your little whatever it is.
This isn't it. Okay, so there's a slight discrepancy between the variable single slit set to 400 microns and the lab slit, which is fixed obviously at 400 microns. There's only a slight difference. My variable slit worked out at 210 fringes per metre, this worked out at 230 fringes per metre. Maybe the truth is somewhere halfway between the two. Tiny fringes anyway, okay? Now this...
So again, just proving the point. So all of this, I mean, I'm just saying it's okay, fine, prove it 600 times, but the argument is that there's clear relationship between the distance between the point sources, the surfaces, and the size of the fringes. That's the key fact. Let's see what kind of gibberish this is.
Crucial information I was trying to give to not only Gary.
So this is just bullshit. I mean, I don't even know why he's arguing this crap. There's no crucial information. Blah 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 blah. I had no interest in whether it's a 200 microns or 500 microns. I don't give a shit. I just cared about the difference between the single slit and the double slit. That was the only thing that mattered to me, because that's the real story here. And the real story was figuring out for all these decades, Richard Feynman and Professor Lewin and all these people, because they keep playing with this stupid, their mathematics keeps playing with this idea of an infinitesimally small slit, that all they were doing was destroying the double slit pattern. They were basically just turning double slits into single slits by destroying two of the point sources, by putting the 2 point sources so close together that they didn't have any relevancy anymore. So that was the clear bingo. Game over moment, was just that realization that there is no double slit if two of the surfaces are so close to each other that you can't create a wavelength of difference between them.
Do with brighter fish, is it? From a distance.
So, who knows? Alright, anyway, enough of that.
Of these slits in this Unilab series of slits the slits are 62.5 microns. That's a bit accurate. 62.5. And 250 slit centers. 250 micron slit centers. So if it's 250 slit centers, then you deduct 62.5. That gives you 187.5 impediment width. Is that right? I've done that right. I've done that right. My math is rubbish. 187.5 impediment barrier. Is that right?
Maybe you ought to figure it out before you do
really
the
should know
video.
that.
Yeah, you should do it before the video.
Okay, again.
Well, whatever. This
It's a
part
very elaborate pattern.
is not very interesting. Okay.
One, as you might imagine, is simply the same as a 2 slit or a 6 slit, just multiplied by 100 or so, equating with those same slit dimensions and the same slit centres. Okay? So that's the same as a 2 slit effectively. So a light through that just gives you the same double slit pattern as a 2 slit, but more like very accurate dots with massive gaps between, okay?
Okay, yes, it has to be consistent with the big envelope is going to be deciding, okay, where the dots are going to be, because the big envelope has to be in the same phase with the littlest dot to have enough light to create the pattern. And only when those two are in alignment can the other ones be in alignment. So obviously those dots have to be spaced pretty far away from each other. Yeah. But they have to match. All of them have to be inside of that envelope. The center of the envelope. The center of the envelope, the biggest node. The smallest node has to be centered on that. And when that happens, then all of the rest of them will line up. All right. So enough of that. Maybe I'll watch the whole video and see if there's anything of interest in it. But it really is just a verification of what I'm arguing. And it's not going to show anything dramatically contradictory to the arguments I made in this video. Alright, so till the next time and such. So I think I'll put this on YouTube just because it's in your face. All you wave people, all you people who think the two-slit experiment proves something or demonstrates the universe has to be a certain way. Well, no it doesn't. Your biggest piece of evidence was always a piece of garbage. And I've basically drawn you at I've revealed, okay, that it's a dumpster. I've opened it, okay, and you can see there's just garbage. Your theory is garbage. If you're going to base it on the double slit experiment, if you're going to say that proves waves, you're in big trouble. It's my argument. Big rational logical trouble. Till the next time and such, so forth and whatnot. This has been draftphysics.com debate physics, but there won't be any counter arguments, not in any kind of rational form. There won't be any links to any evidence, contrary evidence, experimental evidence. They'll just be rhetoric, just a bunch of naysaying, nitpicking, and abuse. So, till the next time and such, and so forth and whatnot.